1 plus Jx circle. So this SWR circle passing through ZL is intersecting this 1 plus Jx circle at 2 points. The first you can see here Z1 and Z2. So from ZL to Z1 and from ZL to Z2, at 2 points it is intersecting. So can we calculate the distance D1 for the first solution? D1 we can easily calculate here. It is 0.209 and here it is 0.329. So the answer for the D1 will be 0.329 minus 0.209 is equal to 0.120 lambda. And we also have to calculate distance D2. So from ZL we have reached in the clockwise direction, we have reached at Z2. So from ZL to Z2, this complete distance we have to calculate. So we can do one thing. This we can calculate at 0.5 because you know one complete circle of semi-arc means 0.5 lambda by 2. So what is this distance? Here it is 0.209 and here it is 0.172 we can take 0.172 minus 0.209. So and so 0.5 minus 0.5 minus, so inside the bracket 0.209 minus 0.172. Here 0.5 minus inside the bracket, so basically it will be equal to 0.5 lambda minus 0.5 lambda minus. So here it will be 0.172 minus 0.208 or 0.209. So 0.172 0.209 minus 0.172. 0.209 minus 0.1. This will be equal to D1 we calculated. D1 was equal to, what was D1? D1 was equal to 0.329 minus 0.2. So 0.329. So this is D1 and D2. Okay, so next we have to calculate L1 and L2. For that you have to find Z1 and Z2. So what is Z1 and Z2? What is Z1 and Z2? So first concentrate on Z1. So Z1 is equal to 1 minus J 1.32 we can take, or 1.33, your wish, 1.32 also we can take. So 1 minus J 1.34. So Z1 is equal to 1 minus J 1.34. So Z1 is this. And what will be Z2 also? You can write for the second solution. So Z2 will be equal to Z2 will be equal to 1 plus J 1 point. What will be the value? So here we have this is 1.3. This will be 1.3. 3 we can take, or 1.34 we can take. So basically it will be equal to 1 plus J 1.3. Here what they have taken? Here it is taken, okay, 1.33. So what will be the stub reactance then? No, negative of this, so that it can be cancelled. So for Z1 solution, so X1 1.34 plus, you can take X2 minus 1. So X1 is equal to 1.34. And in the question it is given, what is given? Open circuited stub. So open circuited stub is given in the question. Open circuited stub 2 we have to travel to plus 1.3. Travel. So open circuited stub on the impedance chart. It is here. So from here to 1.34 we have to travel. So 0.252 in the clockwise direction. We have to travel this much. We can do one thing. We have to basically calculate this much distance, 0.252 this much in the clockwise. Okay. So 0.5 lambda minus, what is this? This is 0.148 we can take, 0.148. So 0.148 lambda, and it is 0.25. So we can write like 0. Actually, it is very disturbing. The students keep on joining and I have to give the permission. So what is wrong? Now I have to talk with. So this is happening with all the classes in Cisco Webex, or that you need permission to join, because previously you were joining automatically without any permission. So this is happening for all the classes or only for this class? Yes, what I am asking? This situation is happening for all the classes or only for this class you need permission?
Only for this class.
Okay, so for other classes automatically you are able to join.
Yes, sir.
So that means in Cisco Webex some setting. So can you, do you know the setting, so that I can change here? So that participants can join automatically. At any time they can join, at any time they can go. I want like that. No permission is required. How we can do that? If you know the Webex setting. Basically, my Webex account is used by one more faculty. What they have done, I don't. Because each time I have to permit. So that is distracting the attention. So, okay, what will be the length of the open circuited stub? L1. What will be L1? So, L1 will be equal to 0.5 lambda minus 0.5 lambda minus 0. It is 0.172 we can take. So 0.172, 0.25 lambda minus 0.17. Okay. So can you solve this and can you tell what is the answer for this? 0. What is the answer? What is the answer for this? How much we are getting? How much we are getting? 0.25 plus 0.1.
0.422.
0.3392 lambda. Is it correct? As per this 0.392.
422, sir.
Huh? This is correct?
422. 0.422.
0.422 you are getting. 0.250, 0.172. So 27542. So basically it will be 0.422 lambda. 0.42 lambda. We have taken 0.25 lambda here. That is okay, no problem. 0.172 we have taken. 0.172. So this is equal to 0.172 or 0.171 also we can take. 2, 4, 6, 8. So if we take 0. But that should not change a lot. So here it is given. What is the answer given here? 0.397. We are getting 0.4. Basically, this is 0.4, but we are getting 0.42. So why we are getting a little bit deviation? Why we are getting this deviation here? We calculated L1. For L1, what we needed? For L1, we needed plus 1.3. And for L2, minus 1.3. If we do for L2, minus 1.34. So we are here, minus 1.34 is here. It is written also L2. Here it is L1 indicated. So, okay. Now, this much, how we can do? 0.1, this is 1.34. 1.34. So, this distance we have to calculate. For the open circuited stub. So what is this? 0.353. 0.353 we can take minus 0.25. So 0.353 minus 0.25 lambda. What will be the value? 0.103 lambda. Here, what they are getting? They are getting exactly the same. 0.103 lambda. So when it is same, so why was a mismatch here? No problem, but because they have not written all the steps that I am doing here, all these things, they have directly written what is D1, D2 direct. D1, D2, L1, L2. So that is not a good practice, and you should also not do directly. You do like how we are doing here, each step is minus this plus this region. Whether it is, whether you are getting 0.4 lambda, 0.397 lambda, 0.422 lambda, 100% marks will be given as per the Smith chart. But write all the steps. Here we are getting exact answer that they are getting. So write all the steps. That is important. Do not write what is written in book, because in book directly they have written the value of L1, L2. At least D1, D2 they have explained, but L1, L2 directly they have done. Here also for this shunt stub, single shunt stub, also directly they have given L1 is equal to this, L2 is equal to this. How it is coming? Okay, so no problem. Next question we will do. This is done. Analytically, you know how to do. Analytical solution you have. So see here, this position of the stub, second solution, 0.103 we were getting the length of a stub. So like this you can do. This is the matching network that you have designed. So now we will do for analytically we have done. I hope so. Analytically I finished for single shunt and single series. Yes, it is done. So now we have double stub tuning. So today mainly we will discuss this topic, double stub tuning. So the first question is why we need a double stub. What was the problem in single stub? So if you look at the single stub circuit, it is here, single shunt stub. So this is the stub position, down a length D from the load, and here we have attached a stub. This is our matching circuit. So suppose we need an adjustable tuner where we can adjust the position of the stub. If we are able to adjust the position of the stub. Because see here, as per this ZL and Z0, we are calculating this is the position and here is the length of the stub. So it is fixed. Similarly for series stub or series stub, so we are calculating the stub position and the stub length as per the value of ZL and Z0. Two solutions are available, that is correct. Both solutions are correct. So for both solution, reflection coefficient also you can calculate. So, but it is fixed because we have calculated a stub position and a stub length. Suppose we need a adjustable tuner and the distance between two stub is also adjustable. So we suppose we need two stub where the distance between two stub This is here indicated D. Here is the stub position. First stub V1, second V2. Distance between them is D. And so can we tune D or adjustable tuner, which is double stub tuner? So D value also we can change, and if we adjust D, so accordingly we have to change V1 and V2, or you can say L1 and L2. Suppose you take D is equal to 3 lambda by 8. Then what is L1 and L2? Suppose second case, you take D is equal to lambda by 8. What is the value of L1 and L2? So basically we can tune it. That is the idea. Because we have more degrees of freedom here. Here, how many degrees of freedom we have in the single stub matching? Here in this case, 2 degrees of freedom. So D and L, that we can change. So here we have 2 solutions. So D and L. Here what we can do? We have L1, L2 and D. L1, L2 and D. So if D is equal to lambda by 8, there will be some other L1, L2, and for D 3 lambda by 8 or lambda by 2 or lambda by 4. So we can calculate L1 and L2. So now one more question: what is the limitation of this system, double stub? It is adjustable, adaptable, that is okay. But what is the limitation of this? See here, limitation is that it is not capable to match all the load impedance to the feed line, transmission line impedance. So this double stub tuner is not capable to match all the load admittance to the feed line, transmission line impedance or admittance. So that is the problem. That is the limitation of this double stub tuner. So now you will ask how this limitation came. So this limitation you will understand if you do the analysis of this analytical solution, mathematical solution. In Smith chart also you can understand, no problem. What is the problem? Just keep on joining. Okay, so now we have to do the Smith chart analysis and also the mathematical analysis, Smith chart solution and analytical. So you are seeing double stub tuner. Here it is YL dash. YL dash is the load admittance. And and this is open or short, that is your choice. Stub you can take, you know that. And this is Y0 or Z0 impedance. Here is also Z0 and Z0, Y0, Y0. So we have to calculate B1, B2 and D as per the value of D. That we have to choose. So YL dash can be transformed this admittance YL dash. Suppose this distance is, suppose it is some distance D load, distance from the load to the first stub. Distance from the load to the first stub. Suppose this is some distance D stub load or D1. So can be transformed this YL dash here at the position of the first stub. That formula we know what will be the input impedance here. So that input impedance will be our admittance, of course. That input admittance. So that input admittance, that will be Y. When YL dash will be transformed at the position of the first stub. If we transform YL dash at the position of the first step. That will be YL. And there is no problem in that also. So basically these two circuits are equivalent circuits. They are same. The difference is that YL dash has been transformed equal to YL at the position of the first step. But here it is a D1 distance away from the first step. That is the only thing. So now this is the original circuit and B is the equivalent circuit. Now when the load is transformed to the first step, we have to calculate V1, V2, or you can say L1, L2. So first we will calculate V1, V2 and then L1. And D we have to decide. D we have to choose. If in the question it is given, then okay. So if we fix the value of D, accordingly we will get L1 and L2. Because if you fix D, then the step position, it is also fixed. If you fix D, accordingly we can calculate L1, L2. Okay, so now you understand this double step tuner here. Here what is happening? So from you keep this circuit YL. So from YL we have placed one stub here, first stub here, and with the susceptance B1. The susceptance of the first stub is B1. Okay, and then D distance we have to travel, and we will reach at the position of the second stub, which is B2. Susceptance B2, and here we have the feed line or transmission line. We have to match Y naught with Y. So basically, we are using Smith chart as an admittance chart. YL admittance should be matched with the Y naught. So what is the distance between the two stubs? That is D. So D distance. So this circle 1 plus JB constant conductance circle, constant conductance circle 1 plus JB will be rotated by an angle corresponding to the D distance. D distance corresponds to how much angle can you tell on Smith chart? D distance on the transmission line will correspond to how much angle on the Smith chart? Lambda distance corresponds to how much angle? 720 degrees. So D distance will correspond, you can calculate that corresponding angle. And we have to move this 1 plus JB circle. So you will be thinking why we are rotating this, because it is 1 plus JB circle and here it is rotated 1 plus JB circle. Both is shown here. This circle is 1 plus JB circle and here it is rotated 1 plus JB circle. So you will be thinking that okay. So can you tell where is 1 plus JB circle in this here in this circuit? When we are saying 1 plus JB circle, what we mean? Because this 1 plus JB circle will be rotated towards because away from the generator. Here is we have generator and towards the load. So away from the generator. How much angle? Corresponding to D distance. Then we can play. So we need a rotated 1 plus JV constant conductance circle. How much rotation? That rotation will be d distance. The angle corresponding to this d distance. That much angle we have to rotate. Then we will reach here. And if we reach here, here we can play because load is here. So this 1 plus JV circle, it is indicated also. See here, it is indicated D. So angle corresponding to D distance, we have to rotate this 1 plus JV circuit. And if we rotate, then we are here. This is rotated 1 plus JV circle. We are at the load. Now we can play. So when we are at the load, no problem. Where is load? Where is YL? Suppose your YL is here, because this is a general discussion. YL is not given to you, the value. It is a general discussion. So suppose your YL is here at this point. So YL is given. So from YL, we have to reach the rotated 1 plus JB circle from YL. So here is the center of the Smith chart. We have reached at Y1 here. Is this the only solution? No, other solution also we have. This is Y1. Y1 or Y1. So then what is B1? Then what is V1? That V1 we can calculate. And for this, what is V1 dash? Y1, V1, Y1 dash, V1 dash. So we are here at Y1. Now again see the circuit. Now what we want? We want to travel a distance d towards the generator. We want to travel a distance d away from the load towards the generator. Towards the generator means clockwise rotation. So d distance clockwise from Y1. From Y1, we have reached Y2, and from Y1 dash, we have reached Y2 dash. So from Y1, we have reached Y2 on this 1 plus JB circle, away from the load towards the generator. Y1 plus JB circle, because when we move, so ultimately we have reached here. So what is the real part of the admittance? Normalized, of course, that is 1. So basically we have started from the rotated circle, and from YL we moved at Y1. From Y1, d distance clockwise away from the load towards generator, we reached here. Here the real part is 1, normalized. The real part will be 1. 1 plus JB circle. Y1 dash also you will reach here only on this circle, 1 plus JB, Y2 dash. But we have to cancel also this value of the imaginary part or the susceptance. We have to cancel with B2 so that we can reach at the center of the chart. See here what happened. Y2 to B2, we are at the center of the chart. Y2 dash to B2 dash, we are at the center of the chart. Now one more thing, you are telling that there is some limitation of this Smith chart. So what is that limitation? That we cannot load, that we cannot match all the load impedance. That we cannot match all the load impedance cannot be matched with the feed line impedance. So why it is so? Because if we are in this region, it is not shaded, but in the soft copy, but hard copy of the book it is shaded. So in this, suppose this G0 you are saying, suppose it is shaded. If I can shade it, then I can. This region I am talking. G0. It is indicated conductance G0. Suppose your load is somewhere at inside this circle, somewhere, anywhere, inside this constant G0 conductance circle. Suppose your load YL, because in this example, in this discussion, we took load at this place. Suppose load is not at this place. Suppose your load is somewhere inside this constant G0 conductance circle. And then my question is, if it is inside this G0 conductance circle YL, then can we reach at Y1? If suppose it is inside, it is here. So then how we will intersect this rotated 1 plus JB circle? How we will intersect? Suppose it is inside this circle, conductance G0 circle. So how we will intersect rotated this circle? You are saying this circle and constant G0 circle. So that means YL there should be some limitation on YL. You cannot match any load admittance to feed line impedance. Any load admittance to the feed line admittance you cannot match. Using this double stub tuner, analytically also easily you can understand. Analytically it is very easy to understand, because you will see, you will get some inequality that is here. That inequality is here. This implies that because GL is real, the quantity within the square root must be non-negative, and so this should be 0 to 1, from 0 to 1. So this implies that GL should be from, so this is inequality, that GL should be from 0 to, otherwise solution is not possible. So mathematically easily you can understand that, okay, any load admittance we cannot match using double stub tuner. There is some limitation. So then you can ask, okay, can we eliminate or can we minimize the limitation? And that is also possible. How? So do one thing, you have any load admittance. Suppose that is inside that circle, conductance circle. So do one thing. You adjust this distance. If you are not able to match, you have to adjust this distance, this one. You can adjust, suppose you see D1, so you can take any value, so that the transformed YL is not inside that constant G0 circle. That is the idea. You can adjust this distance or not. D1, suppose. So that the transformed YL is not inside that G0 constant conductance circle on the Smith chart. So basically the idea will be, we have to change this D1. So that the YL, not YL dash I am saying, YL is not inside the G0 circle. It is outside the G0 circle. That is one solution I told. Then you can match any YL dash. And any other solution you are thinking? Other thing what you can do, in the Smith chart, we have this shaded region inside G naught where we cannot match. So the question is, can we reduce this shaded region? Can we reduce the radius of this circle, G naught circle? Because if we reduce the shaded region, then we will get more value of load admittances to match, where the matching will be possible. So now you will ask, okay, how to reduce this shaded region? So you tell how to reduce. By reducing the distance d, you reduce this distance d. If we reduce the d distance, the radius of this constant conductance circle will be less. But again the thing is, how much we can reduce the d distance? D distance means the distance between two stubs. So we are decreasing the distance between two stubs. That is okay, so that large number of values, load values, we can match. That is the intention. But how much we can reduce D? Because we have to fabricate also. There is some fabrication limit also. Okay, so it should be practically realizable, your circuit. If the fabrication is not realizable because you have reduced D that much, then there is no benefit. So two things I told you. You can decrease the distance D, number one, or you can transform this YL dash if it is inside the constant conductance circle. So you can transform by adjusting this distance from the load to the first stub. These are the two solutions. Either you can change D or you can change. Hope you are getting all this discussion, what is happening here. So it is indicated forbidden region. See here, it is written forbidden region. Forbidden means what? The value of the load, normalized load admittance should not lie inside the forbidden region. Forbidden region is this constant G naught conductance circle inside the circle. This is forbidden region. So this was a general discussion. Now do some specific. So now what could be the value of the distance between two stubs? We cannot take D is equal to lambda by 100 because then it cannot be practically realizable. So what could be the distance? Accordingly, we can calculate L1 and L2. So in practice, we choose stub spacing lambda by 8 or 3 lambda by 8. So lambda by 8, we can choose lambda by 8 or 3 lambda by 8 also you can take, you can choose your wish. If the length of line between the load and first stub can be adjusted, then load admittance YL can always be moved out of the forbidden region. This I explained. Now your job is to solve this question. I will also solve. Question is in front of you using Smith chart. Mathematical we will do later, today only. But first do using Smith chart. Yes, using Smith chart, you have to solve this question. Design a double stub. So in this question, double stub tuner question, we have to design double stub tuner. Load admittance is given. We have to match with a field line impedance. What is the load impedance? Load impedance is 60 minus J80 ohm, 2F50 ohm. So 60 minus J80 ohm. 60 ZL is equal to ZL y Z0 is equal to 60 minus J80 divided by how much? 50. 1.2 minus j 1. This is a small zn. What about the normalized load admittance y? Can we locate that YL on Smith chart? 1.2 minus j 1.6. So where is the load admittance on Smith chart? On Smith chart, where is the load admittance? Already we had done, if you remember, 60 minus j 80. It was 0.3 plus j 0.4. So YL we are interested. Where is YL? YL is here. 0.3 plus j 0.4. So 0.3 plus j 0.4. So where is YL? YL is here. And in the question, what else is given? Open circuited stubs are lambda y 8 apart. Open circuited stubs are lambda y 8 apart. So open circuited, number one thing. Both stubs are open circuited. Lambda y 8 apart means d is equal to lambda y. So lambda is 720 degree. Divide by 8 is 90 degree. 90 degree apart. On Smith chart. On Smith chart. So now come on Smith chart. Where is the rotated 1 plus JB circle that you are doing? 90 degree rotation we need. This is 1 plus JB circle. This circle is 1 plus JB circle. 90 degree rotation. Rotate 90 degree. Here. Here we have the rotated 1 plus JB. So, and YL is here. So, from YL, from the load to this rotated 1 plus JB circle, we are here. Y1 or Y1 dash. So, we have to write what is the value of Y1 and Y1 dash, and also B1 and B1. So, can you tell what is B1? Let's focus on B1 and Y1. That will be. It is intersecting this rotated 1 plus JB circle at 2 points. One is Y1 and other is Y1. So what is Y1? What is Y1? What is B1? What is the value of B1? B1 is equal to 0.4. Here it is 0.4, and here 0. This is 1.7, 1.6, 1.7, 1.75. You can take. So suppose we take 1.75 minus 0.4. What is the answer? 1.75 minus 0.4. So 1.35. 1.35. But here it is 1.31. How? So what is this? Is 0.4. That is okay. It is feasible. What is this Y1? It is 1.6, 1.7, 1.8. So in between, if we take 1.75, I had taken. What is the problem? So what will be B1 as per your observation? I will zoom it more. how much will be V1? Susceptance V1. What will be the value on this admittance chart? V1 is equal to V1 and V1 dash. So 0.40, 0.40 minus 1.7 and 1.8. If we take 1.72 or 1.74, so we have the value, it is 1.32. And what will be V1 dash? Again, what will be V1 dash? V1 dash is here. It is basically here, it is 0.28. 0.28 minus 0.40. So 0.28 minus 0.40. Minus 0.40, it is minus 0.1. Minus 0.12. Minus 0.12. It is 114. I have taken 12. Okay. So B1, B2 is okay. Now again come on Smith chart. From Y1, Y1 is here. B1, B2 we have determined. Y1 we are here. So from Y1 to D distance we have to travel. D means lambda by 8. Lambda by 8 means 0.125 lambda. Towards the generator means clockwise. Go clockwise and reach the 1 plus JB circle in the clockwise. So Y1 towards the generator clockwise on the 1 plus JB circle. It is intersecting at Y2. It is intersecting at Y2. What about Y1 dash? Y1 dash go clockwise. How much? 0.125. It is intersecting at this Y2 dash. So Y1 to Y2. What is Y2? Value of Y2. So Y2 will be equal to 1 minus J 0.3234, 0.34 we can take 0.3, 0.32343638. So 0.34 we can take 1 minus J Y2 will be equal to, this is 3 and 4, na? So 3.3, 3.34. So 1 minus J 3.34. So Y2 is equal to and Y2 dash also we have to write. So what was Y2? 1 minus j 3.34. 1 minus j 3.34. And what is taken in the book or Y2 if they have written 1 minus j 3.38. 1 minus j 3.38. And I have taken 1 minus j 3.34. 3.38 or 3.34. Which is more correct? So 3.2, 3.4, so 3.4. 3.4 I have taken, no? 3.4. 3.34 why I have? It is 3, 3.2, 3.4. Okay, so internet was disconnected. Now it is again connected. So we have written B1 and B1 dash. B1 and B1 dash 1.32 minus 0.12. B2 is plus 3.4. B2 dash is minus 1.32. What will be L1, L1 dash, L2, L2 dash? If both stubs are open circuited. Okay, focus on L1 and L2. One solution. So open circuited to 1.32 we have to reach. Where is open circuit on this admittance chart? Open circuit to 1.32 we have to reach. Where is 1.32 plus 1.32? 1.32 susceptance. One point will be here. So what will be this distance? 0.146. Can we take 0.146? See my dear, 0.146 lambda. Clearly it is written. What I did? Here I have written B1 is equal to 1.32. So open circuited. So from the open circuit we have to reach 1.32. No problem. Okay, remember 1.32. Open circuit you are here to reach 1.32. Where is 1.32? It is here. It is 0.146 lambda. Did you get it or not? Again do for this minus 0.12. Open circuit to minus 0.12. Okay, let us do for plus 3.4. Okay, do for minus 0.12 first. So where is minus 0.12? Can you tell where is minus 0.12? 0.1, 0.12 will be somewhere here. Because 0.1 and 0.2, so 0.12. What will be the answer? 0 point, how much? 0.48 if we take, will there be any problem? 0.48 lambda. What they have taken? This guy has taken 0.482 lambda. 0.482 lambda. I have taken 0.48. You can take more accurate 0.48 or now which is more accurate? 0.48 lambda. Okay. Similarly, for next we have plus 3.4. Plus 3.4. Open circuited to plus 3.4. There is plus 3.4. Plus 3.4. Where is that? Here. 3.4. Because 3.0 and so 3.4 will be somewhere here. What will be the value? What will be the value? 0.33.4. So in between we can take 0.204. If I take, is there any problem? What they have taken? 0.204 I have taken. What they have taken exactly same. 0.204 lambda.